Any general questions, problems, anything? Hey, look, record turnout. the my 5 favorite people. The they're the only ones who come in anymore. We should find a smaller classroom. In the class is big. Good news, bad news. Bad news. I'm not finished grading the papers, as many of you know. The good news is I'm down to 100, which is also the bad news for me. But I'm hoping to have them done this week, especially because this week becomes a good time to start thinking about project 3, which is really about thermodynamics, but also sort of about equilibrium, because they're potentially the same thing. This is another one of those cases where the language that gets used might be different from discipline to discipline. So a lot of people will talk about equilibrium, others might talk about thermodynamics. They're really talking about the same thing. Among the many things I've always claimed, if they put me in charge of Gen Chem for the universe, thermodynamics would be the first thing we talk about, not one of the last things we talk about, because it is really the thing, right? Apologies for the slight blasphemy, but I sometimes refer to thermodynamics as God, right? It is the universe's decision maker, okay? And part of it we do talk about in Chem 1, which is really, if you recall, and hopefully you do, because a relatively quick review of Chem 1 upcoming, right? In Chem 1, we talked about enthalpies, right? We've talked about them this semester as well, but we were introduced to them in Chem 1 as essentially the energy change for a reaction, right? What we haven't done yet this year, but did do in the fall, is calculate the delta H's from a table looking something like this, you might recall, where this first column is labeled delta H's of formation, F for formation. Right. In some sense, and this belittles the importance of thermodynamics, in some sense, we're now going to talk about the other 2 columns in the table. And so, I sometimes say, and I might have said back in the fall, that really Gen Chem ultimately is a whole series of questions relating to a chemical reaction, right? It can sometimes come across as slightly distant in the sense that we don't talk about all the questions relative to a reaction. We talk about all of the questions separate and often apply them to multiple reactions. And so, the second question here was our kinetic issue, right? How fast is it, right? We've been talking about equilibrium of late, and you could even go to how big is the equilibrium, right? Really, the most basic question is, does the reaction even happen, right? After all, other than needing to account for the individual atoms, I can make up any reaction I want, right? I mean, all I'm doing is moving atoms around after all, right? So, I can do this. Just off the top of my head. Does it happen? I don't know. How does the universe decide? All right. And frankly, as we've seen with chemical soup, right, I sometimes have competing reactions, right? In which case, we've been using K to sort out what's most important, right? But if I mix, you know, nitrogen and oxygen, for example, there are a whole lot of different nitrogen oxygen compounds because nitrogen is one of the most labile atoms there is, right? And so if I just mix nitrogen and oxygen together, right, do any of those things happen, right? Does one of them happen? Do two of them happen? Do all of them happen? Right. And so, you know, again, to simplify, dare I say, oversimplify things, right? My general rule of thumb, right, is that if it can happen, it will happen. Right. And by that, from a chemical standpoint, I mean quite literally, mix anything you want. Right. Rearrange the atoms however you want. Call it a balanced equation. It'll happen. All right. Now, that doesn't mean it happens with 100% yield. It doesn't mean it happens fast. Right. It doesn't mean it even happens much at all, especially if something else can happen that's more favorable. Right. But as a general rule of thumb, if you mix things together and they can react, they will. I mean, there's a few rules, right? Mass is conserved, right? For the most part, chemical identity is conserved. I can't turn nitrogens into sodiums, right? That's magic, not chemistry, right? But, you know, if I obey the few rules I have, pretty much any reaction you can write down probably does happen, right? We've been ranking them essentially based on K, right? Which didn't so much say that some things didn't happen, right? As I've been saying all through the acids and bases and the KSP issue, right? All of those reactions have to reach equilibrium, right? But the biggest Ks dominate because they end up representing the biggest change, as you will soon discover over the next few days, right? K is actually slightly fake, right? It's not a thing in any kind of grand physical way. It does end up being a proxy for the thing that is really the thing, capital T, capital H, capital E, which is thermodynamics, right? Because thermodynamics is ultimately the universe's decision maker, right? And the enthalpy thing that we talked about in the fall is the energy part of thermodynamics, right? But it's only part of thermodynamics because there's also this thing called the number of states. Right. And what do I mean by states? Well, I'm glad you asked. Right. If I mix quite literally 1 molecule of oxygen and 1 molecule of hydrogen in an otherwise empty 1 liter flask, right, and I ask how many different states are there, you might be surprised to learn, given that I only have 2 molecules, that I have a nearly infinite number of states. Right? Because of what state actually means. It refers to really 2 things about my system, right? One is the location of the molecules, right? And so this little drawing, albeit in 2 dimensions instead of 3, represents 2 different states of the system, right? On the left-hand picture, you've got an oxygen up in the upper left-hand corner and a hydrogen down in the bottom right-hand corner. Whereas in the picture on the right, you've got a hydrogen up in the upper right-hand corner and oxygen down in the lower left-hand corner. Right. Those are 2 different states of the system. Now, as you can imagine, that alone creates a whole lot of different states because I can just, you know, put this oxygen over here instead of over here, and I have a different state. Right. And so if you think about it, right, I said it was a 1 liter flask. this is a single molecule of oxygen, which is a really, really small thing. And so, there's 100 trillion different places I can put it just along that line, because every time I move it over a spot, it's technically a new state of the system. But if that wasn't bad enough, right, state of the system also includes momentum, right, the velocity of the particle, which is both its speed and its direction. And so even if I had, for a split second in time, the oxygen in the same spot in my flask and the hydrogen in the exact same spot in my flask, if they're actually traveling in different directions, it represents a different state of the system. And so state of the system, right, really represents every possible position and momentum that the molecules can be put in, right? And you might be grinding your teeth because, that seems like a whole lot to deal with, right? On the other hand, even though this system looks simple, I actually picked a system that has way more states than some other systems, as you'll eventually see. And so it's often not that bad. On the other hand, right, it's also not that hard to deal with trillions and trillions and trillions and trillions of states. Right. I just need to crunch them down to something manageable using statistics. Right. And so we won't do the hardcore statistical analysis in here. Right. But, you might, if you're a chem engineer, take statistical mechanics later. You might not, I don't know. I forget. But there is some relatively hardcore probability statistics you could do on the ensemble to crunch it down to the most probable states of the system, as opposed to having to deal with all the individual states of the system. Right? For us, the numbers have already been crunched. Right? And so I have two pieces to my thermodynamics. Right? There's my states piece, which we'll probably get to mostly on Wednesday. And then there's my energy piece, right, which is actually our old friend delta H. Right. Now, most everything I'm going to say for the next, 20 minutes or so, should be a review. To that end, I may go a little quickly. It may be more or less of a review for you, depending on what your Chem 1 experience was. And so please stop me if I'm going too quickly. Right. Because while this should be review, most of the important pieces of the enthalpy puzzle also apply to the rest of my thermodynamic puzzle. And so if we can recall how we handle delta H, right, it makes the rest of the thermodynamics really easy to handle. Okay, and so our old friend delta H, it's called enthalpy. Again, it's essentially energy under a certain set of conditions, right? And again, for sign convention, if nothing else, right, the enthalpy change for a process is defined as the difference between the final enthalpy and the initial enthalpy in a system, right? In general, by the way, of course, the final state for a chemical reaction is usually the products, whereas the initial state's usually the reactants. Right? Enthalpy is really defined more generally. It's not strictly chemical, mind you, but for a chemical reaction, The final state is the products, and the initial state, the reactants. All right. And again, ultimately, the only thing that really matters here is its enthalpy. All right. Again, this is a case where my variable has a whole lot of subscripts, right? The subscripts are just giving me specific information about what's really a single concept, all right? Which brings us back to what I keep referring to as the most important diagram of all of general chemistry. I believe that to be true. All right. It's also a big piece of the thermodynamic puzzle. And hint, hint, nudge, nudge, might therefore be relevant to Project 3. All right. And again, especially in the context of what we were just talking about, this diagram grossly oversimplifies what the real reaction looked like, right? Because the reactants, whatever they might be, don't all have exactly the same energy, right? We were just talking about the issue here, right, of my hydrogen having different velocities, right? Enthalpy isn't strictly kinetic energy, but kinetic energy is a piece of enthalpy, right? And so those two hydrogen atoms, right, do not have identical enthalpies because they have different kinetic energy. And so when I draw this diagram, right, what it really represents, right, is sort of that statistically most probable pathway, right? This is really a multi-dimensional surface because each of the reactants has its own enthalpy, right? There's a distribution, right? Each of the products has their own enthalpy. There's a distribution, right? This is just the most probable position on both the product and reactant side. And so really, if I were to draw this, you know, it's often referred to as a 10 to the 23rd dimensional surface, right? The other way to think of it is there's thickness to my line, right? Because some of my reactants are up here and some of my reactants are down here and everywhere in between. So, you know, it becomes really ugly in a hurry, right? But this thing is really not this single smooth line where everybody has the same energy and everybody travels the same journey, right? Because if I'm up here instead of down here, that means my whole journey through this whole envelope, it could be different, right? But, right, that issue aside, right, as again, a most probable journey as represented, it shows me, right, really two key pieces of the energy profile for a chemical reaction, right? I've got good old activation energy, which of course is the kinetics piece of it. Right. That energy change is transient, of course, right? It's part of my journey in going from reactants to products, but, you know, a lot of that uphill is compensated by the downhill on the other side, right? And so the other big piece of this is the delta H, which is again just the difference now between the products and reactants. That's a net energy difference between the products and reactants, and to some extent represents stability. As we'll talk about shortly, lower energy, generally more stable. Right. This is also, right, the initial and final difference that cares not how long it takes to get there, right? Which is why, you know, this piece up here is all about the kinetics. That is different, right? Not completely unrelated, but mostly unrelated to the issue of stability, right? Which is part of the way, you know, we were talking about K. It's a balance between the products and reactants. Right, a big part of that balance is this enthalpy difference. Right, and so the activation energy determines how fast you get there. Right, the enthalpy difference determines what your relative stability is on the reactant and product side. Those are two very different things. Right, in the long run, you should end up in the more stable position. Right, but that could happen in a second, or that could happen in a million years, because my stability is defined by this energy difference, whereas my kinetics is defined by this energy difference. And they are really mostly decoupled, right? I mean, sometimes, like with my endothermic reaction, right, this delta H energy appears to be part of the activation barrier, but of course, that's only true in the one direction. Right, as we talked about with equilibrium, these pictures are really reversible. If I flip this picture over, I get this picture. Right. And so even though, you know, in this picture, the delta H and the activation overlap, they don't in reverse. And so this whole, you know, rate is very different than my net stability. Right. And so, you know, for any of my reactions when I'm talking about reaching equilibrium, I never said how long it takes, right? For a very slow reaction, it can quite literally take billions of years to get to equilibrium, right? A good example of that is diamond formation, right? Even if you have the right conditions, hot, deep in the center of the earth, right? For the product, diamond to form takes billions of years, right? And so getting to equilibrium is all about your net balance. How fast you get there is all about the activation energy. They are two different things, right? And there's a lot of different kinds of energies in my system, right? There's energy in the bonds. There's the kinetic energy we already talked about. The molecules are moving around, right? There's interactions with other molecules in the system, right? In some cases, solvent molecules or other reactants, or even the molecules themselves. There's no reason why a hydrogen doesn't interact with another hydrogen, right? Part of that is my quote unquote intermolecular forces, right? Energy is force acting over a distance. And so there's a whole bunch of different energies in my system, right? The one big energy rule, right, and really in some sense, one of my two biggest rules for the universe, of course, is that energy is conserved, right? And so in all of these processes, I'm mostly just moving around the energy, right? My bond energy comes and goes as I make and break bonds. That could turn into kinetic energy, right? My kinetic energy could be used to break the bonds, right? But in the end, all I do is move the joules around. And so again, this is really a statistical, right, most probable pathway in energy for the molecules. In point of fact, if you take any single molecule in the system, it may not be on that line at all. And it's almost certainly not on the line the whole time, right? Because again, that entire line is sort of a statistical average, right? And, right, we talked a little bit, even this semester, about exothermic versus endothermic reactions, right? This is really just a sign convention, but the sign does tell you which way the energy is going, right? And so since I'm always final state minus initial state, right, if it's negative, it's because the initial enthalpy is bigger, right, than the final enthalpy. right? On the other hand, for an endothermic reaction, here's my products, they're up high, here's my reactants, they're down low. I'm going to have the opposite sign, right? Because now the final, which is my products, is bigger than the initial, so big number minus small number is always going to be positive. Right. And so that really becomes, right, a question of the system and the surroundings, right? The delta E for the universe is always 0. But that doesn't mean there's not exchange in energy between the system and the surroundings, right? And so the chemical reaction itself is usually viewed as the system, which is why I'm just talking about the enthalpy of the products and the reactants, right? Other things like air in the room, right, solvents, and the like constitute the surroundings. And so that's really a question of equal but opposite amounts of enthalpy or energy. So if this delta H is negative, right, the surroundings have to be positive to balance it. Really, I should go with delta E instead of, because it doesn't have to be enthalpy per se. It could be all heat, for example. Right. And again, you know, I use this diagram in Chem 1, I copy it here, right? Ultimately, right, collisions get me up and down the hill in terms of energy, right? Energy is conserved for the entire system and universe, right? But that doesn't mean an individual molecule can't pick up or lose energy as long as it's balanced by a different process. So again, the actual pathway for a molecule is a tortured random process where I just keep bumping into things. And so if I bump into something and pick up energy, I go up here. If I bump into something and lose energy, I go back down here. And so my journey up here is a whole lot of up and down, up and down, up and down, until by some small miracle I get to the top. Once I'm at the top, I actually have a 50% chance of going each way, right? Because my next collision is going to start me down the hill one way or the other, right? And so it is nearly miraculous that most reactions happen. But again, you've got statistics on your side. You've got 10 to the 23rd molecules zipping around and bumping into each other. Even though the journey is tortured, there's a whole lot of collisions per second, right? Which, you know, if you think back to Arrhenius, that's really embedded in the collision frequency factor. And you might recall, you know, numbers for these things are often 10 to the 14th per second. All right. Okay. And so that's why that whole hill represents the speed thing. Ultimately, my enthalpy is just the difference between where I started and where I end up. Right. And enthalpy is just that. Again, it gets a whole lot of subscripts, right? For similar reasons to why we had all those subscripts with our equilibrium constants, right? They are attempting to give you more specific information about exactly what the enthalpy represents, right? And so, you know, delta H, they're all the same. The subscript should tell me something different. So sometimes the subscript represents a reaction, right? Sometimes very specifically, right? You can have a delta H of combustion if your reaction's combustion, right? You can have a delta H of photosynthesis. Whoops, it's a delta. Right, the subscript's only trying to tell me what the reaction is. It shouldn't change what enthalpy is or how I deal with it. Right. The two most useful, and really in some sense the two most specific indicators, right, are my superscript 0 which represents standard conditions. So mostly my usual standard temperature and pressure. There is actually a third standard condition, which we'll talk about in a minute, right? But if I have delta H raised to the superscript 0, I am simply telling you the temperature and pressure under which this process occurred. Right. And you will be unsurprised to learn, of course, that different temperatures do have an effect on the delta H value, and for gas phase reactions in particular, different pressures can have an effect on what the delta H is. So temperature and pressure matter, and again, just to have a standard set for measurement, good old delta H superscript 0. All right, and the other key little indicator is the subscript F. This is really one of my specific reaction types, right? It's really delta H, F for formation. Right. That's really referring to a specific reaction type. It is also, I know how much you love when I do this, but it's only 30 slides. It's also, you might notice, right, how that first column in my table of thermodynamic variables is actually headed. Right. Those are enthalpies of formation for those individual compounds. They actually don't apply to the compound, right? That is not the enthalpy of nitrogen, right, or ammonia. What it is the enthalpy change involved if you actually undertake the reaction to make ammonia or to make nitrogen, which by itself would be very limiting and restrictive, right? I mean, the number of times I want to make nitrogen relative to the number of times I want to use nitrogen to make something else is a relatively small number, right? On the other hand, what really operationalizes good old delta H of formation is what is fundamentally the most important property about delta H, right? Hands down, no argument. Right. The most important thing about enthalpy is that it is a state function. Right. And state functions are sort of non-intuitive, mostly because the world we live in is not a state function. Right. A state function is something that depends only on where you start and where you finish. It does not matter how you get there, right? As I say, this is non-intuitive because it literally means the only thing that matters is I started at my house and ended up here. It doesn't matter if I drove here or walked here or crawled here. It doesn't matter if I was dragged here by a team of angry horses. It doesn't matter if I started by going the wrong way and went all the way around the globe and ended up here. All right. If my journey were a state function, and clearly it's not, I would be a little late for class. You know, if I came here by way of, I don't know what's exactly opposite me, Russia, you know, Europe, and then back around. All right. In our life, the path usually matters, right? But for a state function, it does not. Start here and end there. No matter how you get there, right, the difference is the same. You could look at altitude as representing that, right, in some sense, right? Even then, we could argue that it matters how I get there, right? But not for the altitude, right? If I start at the bottom and I end at the top, no matter how I got there, the difference in height is the same, even if the journey itself was more tortuous, right? And enthalpy is like that, right? It doesn't really care how you got there. It only cares where you start and where you end. That is a very useful function, right? Because now it really means I don't have to do the reaction to know what the enthalpy change is for the reaction, right? And so if this is a brand new reaction nobody's ever done, right, and I want to know the delta H for that reaction, right, that technically has to be the difference between my reactants and my products. And so most directly, if I do the reaction and carefully measure the energy change in the system, right, I get the value, right? And of course, if I'm trying to measure it, that's usually what I would do, right? Unless there's something really difficult, unusual, or dangerous about doing the reaction itself, right? If I really want to know the delta H for the reaction, I'm going to have to measure it at some point, right? But because it's a state function, it doesn't actually matter if I go from the reactants to the products directly, right? That's a one-step reaction. I could do this seven-step reaction instead. I go up here, make something new, I make something new, I make something new, I make something new, I make something new. Eventually, I end up with the right products, right? And you might say, and it's a perfectly logical thing to say, why would I ever go the seven-step route instead of the one-step route, right? And the answer is, if you know what the 7 steps are, right, and you don't know what the one step is, it's actually easier to take the path you know than to undertake the path you don't know. Right. And where this is useful is when I couple it with my delta H's of formation. Right. If I want to do this reaction, technically speaking, right, the process I'm looking for is for water and dinitrogen trioxide to be in a beaker and react, and apparently with 100% yield, right, give me hydrogen nitrite, right? But I don't have to actually do that reaction to know what the enthalpy change could be, because it's a state function. And the one pathway I always have available to me is the delta H of formation, right? Because, right, I can make water and dinitrogen trioxide from elements. And I could separately make the hydrogen nitrite from elements, right? And so essentially I started here and I made these, and I started here and I made these. The number I'm looking for actually completes the circle, right? And so my pathway to calculating the missing leg is essentially to take this journey around the circle where the total delta H is 0, right? Essentially, I started with just elements at standard temperature and pressure, and I ended up with the same elements at standard temperature and pressure, but I did a bunch of chemical reactions along the way, right? And so to that end, if I know my delta H is a formation, which is the amount of enthalpy involved in taking these elements and turn them into that molecule, I know all but the one leg of this cycle, and I can calculate the delta H for the overall process by subtracting essentially the delta H of formation of the products and the delta H is of formation of the reactants. Right? Yes, no? Well, we'll calculate some apparently Wednesday, right? Now, that's a big piece of my thermodynamic puzzle, right? And what I said a moment ago is true. Generally speaking, lower energy is more stable. Right. Which means if the universe is trying to settle into its most stable configuration, it should always opt for the lowest energy state. If that were true, water would never evaporate. Right? In fact, moisture in the air should be constantly condensing, right? Because liquid water at room temperature is lower in energy than gaseous water at room temperature. Right? If nothing else, there's the phase change enthalpy I need to overcome. Right? Yet, I'm pretty sure no one will argue with me if I say, right, water evaporates all the time. You've seen it, right? If there's a bird bath in your backyard that's suddenly empty, it's not because the birds got thirsty. If you leave a glass of water on a shelf somewhere and forget about it, you come back, the volume's lower, right? Water evaporates even though it is energetically unfavorable, right? In fact, if molecules were really trying to get in their lowest energy state, all of my water should be spontaneously freezing, because that would be a lower energy state than being liquid at any temperature, right? Yet it does not happen, right? And the reason it does not happen is because energy isn't the whole story, right? It's just a piece of the story, right? Sometimes it's the most important piece of the story. Sometimes it's the least important, right? So if you take my favorite reaction, right? Again, I could measure the enthalpy change for that reaction. In practice, I don't have to. Right. Because I do have available to me the fact that enthalpy is a state function, and so I can pick a pathway, right, that allows me to know what the delta H of the reaction should be based on the known delta H's for the other reactions, right? And it would be really simple if I just had a table of enthalpies, right? Because ultimately, if I just take the enthalpies of the water and subtract from them the enthalpies of the oxygen and the hydrogen, right, I would have the enthalpy change for the reaction, right? The problem is, it is nearly impossible to determine the absolute enthalpy of anything because of the sheer number of different energy terms that go into it, right? At some point, you've arguably got relativistic mass energy in there on top of nuclear energy, on top of chemical bond energy, on top of kinetic energy. Enthalpies aren't really known, which is why my enthalpies are always measured as delta H's. And so again, right, I could do that process and measure it, or I could make the products out of elements, and I could make the reactants out of elements, and I could subtract the difference between those two pathways to essentially complete the circle, right? And so, right, if I go to my appendix in the back of the book, or of course your favorite table of thermodynamic variables on the internet, right, I will find something that looks like this, whoops, right, where this first column is delta H's of formation. Again, those are the enthalpy changes involved in making the molecules out of elements. So, you know, pick something down here, right? N2O4 as a gas, you'll notice, right? The elemental form of nitrogen is nitrogen. The elemental form of oxygen is oxygen. And so the formation reaction for N2O4 is one nitrogen reacting with two oxygens to give me N2O4. All right. All right. This number corresponds to the delta H for this reaction. Whoops. All right. It is not the enthalpy of N2O4. It is the enthalpy change involved in the reaction that makes N2O4 out of standard temperature and pressure, standard elemental forms. Right. And so, given that, I'm doing this, right, where I start here and I make hydrogen and I make oxygen and I make water and then I subtract the two. Right. In terms of the table, that means I am summing all of the delta H's of formation for the products and subtracting from that the sum of all the delta H's of formation for the reactants, right? Because that gives me the difference between those two pathways as I'm trying to complete the circle. This is my missing leg in that cycle. And so there's my delta H's of formation. You will notice, of course, for this particular reaction, oxygen's a 0 and hydrogen's a 0 because, of course, if I'm making an element out of elements, there's no change in enthalpy, right? Oxygen is an element, you know. There's no point in even writing the formation reaction. It's already just formed. So the delta H's of formation of elements, standard elements, are always 0. And water, phase matters, right, has a delta H of formation like so. And so my calculation for water is a little bit boring, right? Stoichiometry matters. So 2 times the delta H of formation of water minus technically 2 times the delta H of formation of hydrogen plus the delta H of formation of oxygen. Again, since hydrogen and oxygen are both already in their elemental forms, they're just zeros. Right. Water in the gaseous form, because phase matters, is minus 241.8, which gives me a grand total for this reaction as written of minus 483.6 kilojoules. Right. And this is as written, meaning, right, this is minus 483.6 kilojoules per 2 moles of water, if I want to talk about water. It's also minus 483.6 kilojoules per 2 moles of hydrogen, if I want to talk about hydrogen. And of course, it's minus 483.6 kilojoules per 1 mole of oxygen, if I want to talk about oxygen. Right. In the end, the amount does matter, but the delta H for the reaction is often written just in kilojoules, because then I could talk about either one of the 3 species I wanted to. And so that reaction is negative, which means it's exothermic, which means my water is more stable than my hydrogen and oxygen separately. All right. But, right, energy changes aren't the whole story. If they were, hydrogen and oxygen would be spontaneously turning to water all the time, which means, by the way, there'd be less oxygen in the air since there's hydrogen in the air, and they'd all be reacting to form water. Right. And more to the point, right, water should never evaporate if energy was the whole story, right? And it's not, the other part of the story, right, is my allowed or number of states for the system, right? And that will be Wednesday's task, right? In a word, by the way, right, it's entropy, right? Entropy is a measure of the number of states of the system, which we'll talk about on Wednesday. If you have questions or problems, I remain here for a few moments. If not, happy Dingus Day.